All right, let's talk about that big machine learning interview you've got coming up. Today, we're not just going to go over Bayesian statistics. Nope. We're going to transform you into that candidate who can walk in, sit down, and absolutely crush any question they throw at you on the topic. Let's get started.
So picture this. You're in the interview. It's going well. The hiring manager leans forward, looks you in the eye and says, "Let's talk about the Bayesian approach to machine learning." This is it. This is more than just a tech question, you know? It's a probe into how you think about uncertainty, about data, about learning itself. So, let's build the perfect answer, starting from the very core idea. Okay, the first thing you need to explain is the fundamental shift in perspective. It all comes down to what you think is random. For a frequentist, there's one single true answer out there in the universe, like the one true click-through rate for an ad. It's fixed. The data they collect is what's random. So they ask, given this one true rate, how likely is the data I just saw? A Bayesian? They flip that completely on its head. The data you have, that's a fact. It's fixed. It already happened. What's uncertain, what's random, is the parameter itself. So they ask, given the clicks I just saw, what's my new belief about the range of possible click-through rates? It's a really profound difference.
So you've laid out the philosophy. How do you actually put that into practice? Well, your answer has to start with the one equation that governs this entire world.
This right here, this is your home base. You explain that your updated belief, which we call the posterior, is basically a blend of two things. First, there's the likelihood. That's where you ask, how well does a certain parameter value explain the data I just saw? And second, there's the prior, and that's your belief about the parameter before you saw a single data point. It's literally just taking what you already thought and updating it with new evidence.
And it's not just a one-and-done calculation, right? It's a learning process. You start with a guess, your prior. You collect some data, which gives you the likelihood. You mash them together and get a new, smarter belief, the posterior. And here's the really cool part. That posterior you just calculated, it can now become your prior for the next round of data that comes in. It's this beautiful, continuous cycle of getting smarter.
The interviewer is nodding along, impressed. But now they hit you with the practical question. Okay, so how do you, actually compute that posterior? This is where you show you've actually done this stuff. You start with the clean, elegant answer, conjugate priors. You can think of this as playing Bayesian statistics on easy mode. It's when you pick a special prior that plays nicely with your likelihood. When you combine them, the posterior ends up being the exact same type of distribution as your prior. A beta distribution stays a beta, a gamma stays a gamma. It just gets updated parameters. It's an awesome mathematical shortcut when you can use it. And the absolute classic example you should have in your back pocket is the beta binomial case. Let's say your prior belief about a coin's fairness is a beta distribution, and then you go and flip it a bunch of times. That's your binomial data. Well, your new updated belief is also a beta distribution, and updating it is super intuitive. You just add the number of heads and tails you saw to the parameters. It's as simple as adding counts.
But let's be real. In the messy world of machine learning, with complex neural networks, these neat little shortcuts, they pretty much never exist. The interviewer knows this, and this question is your cue to bring out the big guns, the tools that modern Bayesians use every single day.
And you explain that there are really two main workhorses. First, you have MCMC. That's Markov Chain Monte Carlo. This is a sampling method. It's slow, it's methodical, but if you let it run long enough, it will give you the exact shape of your posterior. It's the gold standard for accuracy. But what if you have a massive data set and you don't have forever? That's where variational inference, or VI, comes in. VI cleverly turns the problem into an optimization task. It tries to find a simpler distribution that's as close as possible to the true, complicated posterior. It's way, way faster, but it is an approximation. The key point you want to make is that this is a classic engineering trade-off. Do you need absolute precision or do you need speed and the ability to scale?
Okay, you've nailed the math, you've nailed the methods. Now it's time to elevate your answer and show that you understand the deeper philosophical side of this, especially when it comes to explaining your results to, actual humans. This is a game-changing distinction to bring up in an interview. The real power of Bayesian methods is how you talk about uncertainty, and it all comes down to the credible interval. Look at the Bayesian interpretation. A 95% credible interval means there is a 95% chance the true answer is in this range. That's it. It's simple, direct, and it's exactly what everyone thinks a confidence interval means. But it's not. The frequentist confidence interval has that weird, convoluted explanation about repeating an experiment 100 times. For communicating results to business stakeholders, the Bayesian version is just clearer and way more intuitive.
You're doing great at this point. Seriously. But if you really want to blow them away, you need an ace in the hole. And that is Bayesian model comparison. This shows you're not just a technician. You're someone who can use this framework to make smarter decisions.
And you should be 100% ready for this follow-up. It cuts right to the heart of why so many people are ditching old-school statistical tests for a Bayesian approach when making important decisions.
Your answer here is all about something called the Bayes factor. And it's a beautifully simple idea. You just calculate how probable your data is under Model A, and you divide it by how probable that same data is under Model B. That's it. The ratio you get tells you exactly how much the evidence favors one model over the other. A Bayes factor of, say, 10 literally means the data is 10 times more likely under Model A than Model B.
And this simple ratio leads to some huge advantages over p-values. You're not just testing against some vague null hypothesis. You're directly comparing two real models you actually care about. You can toss out that arbitrary p less than 0.05 rule. And my favorite part? It has a built-in Occam's razor. The framework automatically punishes models that are too complex, naturally favoring the simplest explanation that fits the data.
You've absolutely nailed it. You've walked the interviewer all the way from the core philosophy to the practical tools to advanced applications. So let's just do a quick, rapid-fire debrief to lock in the key talking points.
Let's run through it. Posterior, that's your updated belief after seeing data. Conjugacy, that's your handy math shortcut. The map estimate, that's when you need a single best guess for your parameter, but it's a smart guess that's been regularized by your prior. The credible interval gives you a range for your parameter that has a simple, direct probability attached to it. The Bayes factor compares the evidence for two different models. And finally, the posterior predictive is your tool for forecasting. It gives you a whole distribution of possible future outcomes, which fully accounts for your uncertainty. Got it? Good. So as you're wrapping up that interview, just remember this. Getting good at Bayesian statistics isn't just about memorizing some formulas. It's about adopting a whole new and I think much more powerful way of thinking about uncertainty itself. And that is the skill that's going to make you an incredibly valuable part of any ML team. Go get 'em!